Hey everybody, it's 3 o'clock, it's Tuesday, that means it's Tech Tuesday. Today I'm going to be talking about Wi-Fi 6E. The E stands for exciting. That's not really, but I'll be right back. Thanks for joining me again. This is Rick Usey. It's Tech Tuesday, and I am talking about Wi-Fi 6E today. The E actually stands for extended. What they've done is Wi-Fi 6 has been out for a little while now as a new Wi-Fi standard, and they've now extended that. They've made it official that they've extended that into the 6 gigahertz spectrum band. So that really is exciting. But the E stands for extended. So that's what I'm talking about today. So let's start with just a quick review of where we are and how we got started. So first, again, this was a landmark decision by the FCC just a few days ago. One reason it was landmark, I think, is because it was a unanimous decision, which you don't always find in the FCC. A lot of times it's partisan, but in this case, all of the commissioners voted for this just a few days ago. So this now is a report and order from the FCC. And again, let's look back a little bit on where we have been and where we are now. So the Wi-Fi standard, first standard 802.11 back in 1997, and it's grown since then. You see all the iterations here up until 2019 when we had 802.11ax. And it says here 2.4 up to 6 gigahertz, but at this point, when this was ratified in 2019, they weren't sure whether 6 gigahertz would be used because it hadn't been approved yet. But they kind of worked it into the specification where it could be. So they've now designated this as Wi-Fi 6E, again for extended. So originally they knew it was going to be 2.4 and 5 gigahertz, which are the same frequencies that we have available today with Wi-Fi. A lot of people have dual band routers that operate on both. But the difference with Wi-Fi 6, when it was first developed, was that they'd be using that spectrum in a more efficient way, which was actually quite a big deal. Basically, you can see some of the things that it added here. So it added some things that would allow you to use the spectrum more efficiently. OFDMA, target wake time, BSS coloring, MU-MIMO on the uplink. So these are all things that make the communication between the access point and the client devices more intelligent. They can actually communicate with each other better, and they can coordinate better so that you can use the spectrum a lot more efficiently. I'm not going to go into Wi-Fi 6 and all those specifics because I did a broadcast on that a little while ago. So if you're interested in that, just go back. Actually, you can look in the comment section down below. I pinned a comment there with a link to that previous broadcast on Wi-Fi 6 where I go through all of those improvements on how the access points and the clients talk to each other, the things that make it more efficient use of the spectrum. So today we're going to be focusing more on the 6 gigahertz side of this and adding that additional spectrum into the mix. So Wi-Fi 6E, again, it extends into the 6 gigahertz band, really more than just the 6 gigahertz band. It's from 5925 megahertz up to 7125 megahertz. So it's 1.2 gigahertz of spectrum, or 1200 megahertz of spectrum that they've added to Wi-Fi. That's a huge amount. Pretty much really more than triples the current available spectrum that we have for Wi-Fi. And as you probably know, Wi-Fi can be really congested. And you think about all the people, right now in history, that people are home with pandemics, and there's a lot of people needing access to Wi-Fi from their homes, and lots more devices connecting. This is especially the case, especially important in areas like apartment buildings, those kinds of things, which we'll talk about. So this is a really big deal at any time, but especially now. We've seen the real need for Wi-Fi. In addition to the 1.2 gigahertz and the 6 gigahertz spectrum, there's very low latency, 2 millisecond latency, which is very important for some of the applications that they're thinking about doing, some of the future applications that they want to do in Wi-Fi. And then, really important, it's available for unlicensed use. So the FCC has made this entire band available for unlicensed use, for low power indoor use, and then 850 megahertz available for unlicensed use for outdoor standard power antennas, which we'll talk about. So that's a really big deal as well. So with this large amount of spectrum, you can have actually up to 160 megahertz channels right now as it's defined. So that would be 7 160 megahertz channels or 14 80 megahertz channels. So that gives you very wide channels. They're going to be able to transmit lots of data all at once from lots of different devices that might be connected. And there's a path to 320 megahertz wide channels in this. That would probably be Wi-Fi 7 when they do that. But for right now, I believe it's going to be limited to 80 or 160 megahertz channels on this spectrum, on this particular band. So let's talk about the standard power antennas. These would be those that you can use outdoors. And because there are incumbents in this band right now, they needed to come up with a way to protect those incumbents. And those would be utilities that are using this band right now, public safety kinds of operations, point-to-point microwave links, fixed satellite services, radio astronomy. All these are incumbents that are using the band, and they need to be protected from interference from new Wi-Fi devices that would be in this band outside. So for the outside, it's going to require something called an Automated Frequency Coordination System, or an AFC. You can't quite see the C there on my slide, but that's going to be something that is very similar to what they've done with TV white space, where the same kind of thing, when they wanted to allow TV white space to be used for broadband, they needed a way to manage the interference and to be able to have a way to control who could be using the spectrum when there was an incumbent in the area. And this was kind of modeled around that. This AFC was modeled around that. It's also similar to the SAS systems that I was talking about recently with CBRS, where you've got the Citizens Broadband Radio Service or system, where you've got Navy ships that are coming in and out of port and around shore that need to be protected from interference. It's a little bit different in that the CBRS model uses dynamic spectrum sharing, where these SAS databases will look at the spectrum and they will only exclude an area if there happens to be an incumbent transmitting at that time. So again, Navy ships moving around all over the place. You might be using a particular bit of spectrum and be allowed to use that and allocated that by the SAS system, kind of like the AFC. But if a Navy ship comes into port, then you would be required to back off of that for some period of time and move to a different part of the spectrum. Well, in this case, most of the people that are using these incumbents, I mean, they're fixed kinds of deployments, microwave, point-to-point, kind of deployments that are pretty much up most of the time or all of the time. So these AFCs will require that that these incumbents be protected, and it basically will register. It'll be like a centralized database that will register all of these APs that are out there, and it will let them know which incumbents need to be protected, what frequencies they're on. So it's going to calculate basically these exclusion zones that are going to be pretty much permanent. That can change obviously over time, but this will be set up to protect operations in Canada and Mexico also, if you've got some access points near the border, but of course all around the United States. They're going to take into account the antenna height and other propagation kinds of data from these access points, and that will help them determine the exclusion zones that are required based on that antenna's height and other qualities. There's no professional installation required. And again, unlike CBRS, where if you're going to have an outdoor AP, you have to have it, if it's a certain height, you have to have it professionally installed to make sure that you've got everything aligned correctly. In this case, they're not requiring that. They are requiring that these devices be able to geolocate themselves. So they have to have geolocation data, and that's going to take the place of the need to have this professional installation required for these APs that are outside. The AFC is also supposed to take into account any lower power levels that these APs are using. So if an AP is going to be broadcasting at the maximum power, it's going to have a wider exclusion zone. But if the APs are broadcasting at a lower power, then they can restrict that or close in that exclusion zone a little bit so that there's a little bit further range that those lower power devices can send, or lower power transmissions. And then the APs, I put APs here early, it is APs. So the APs have to check the frequency availability daily. So again, it's mostly going to be not changing very much, but if there's a new incumbent that comes into play, a new microwave link or something like that, then they will be added into the AFC database, and the APs need to check on that daily just to make sure that they don't interfere with a new incumbent, or if some change happens with an existing incumbent. And as far as new incumbents, they can, there's a provision in here where they can be registered in the AFC database while their application is still pending. So it's not like they're going to go live and then have to worry about getting everything up to date. So they can have a pending status, and then they will be automatically in the AFC database. And the access points will then need to check daily to make sure that they're not interfering. So again, on these standard power antennas, they can't be used currently in what the FCC has proposed in mobile kinds of applications. So they can't be used in a car, in trains, ships, or small aircraft. That doesn't mean that you can't take your mobile device outside and connect to a 6G, excuse me, a Wi-Fi 6 gigahertz kind of access point. It just means that you can't be driving around the car and expect to be roaming, for example, on this. It's not going to be in use for mobile. So you can take your iPhone out, your laptop, or whatever, and connect to these devices. Portable, transportable is okay. And they can be used in large aircraft that are flying above 10,000 feet, because the FCC sees that as not really being an issue for interference. Airplanes already do a lot of, the signals don't propagate very well outside of the airplane, just like they would be in, let's say, a home. And actually, it's worse in an airplane as far as propagating outside the environment. So there's also low-power indoor antennas, and the beauty of this is they can use all 1,200 megahertz of the spectrum. So they can use the complete spectrum. So this would be great for indoor uses: smartphones, tablets, laptops, IoT devices, whether that be in a home or in a manufacturing facility or whatever. You've got all of this spectrum now available for indoor use. It's lower power, and they wanted to make this low enough power where you didn't have to then have all of these indoor devices have to be registered or communicating with an AFC database to decide, which frequencies can I talk on. So that's not required in this case. So it's low power, probably high enough power to be able to get through most medium average size homes, let's say, in the United States. If you have a device that's centrally located, or maybe in a home that is situated a certain way, you should be okay. Although it may be that as people implement this Wi-Fi 6E in their homes, that they'll do mesh networks to be able to get really fast access everywhere. But for these low-powered indoor devices, no AFC required, and they can use the entire 1,200 megahertz of spectrum. There are some hardware requirements that the FCC is putting in place to try to make sure that people don't take these devices and make them really more high-powered devices. So there's hardware requirements for these low-power indoor antennas. First of all, the design of the antenna has to be integrated. So you can't have an external antenna or an antenna that you could modify by putting some other high-gain antenna on top of it. So it's supposed to be integrated in that way. It's supposed to require that it be a powered device, external power, so no battery, because again, that would make it less likely that it'd be something that you would take outside. No weatherproofing, so you can't have this hardened and in a shell that would be weatherproof. Again, the idea being that it's supposed to be protected indoors, and that's not required. And then the labeling on the device and the manual has to say for indoor use only. So again, these are really meant to be indoor antennas and not meant to be used outside. And part of the reason of this, again, is that with Wi-Fi in this 6 gigahertz band, it's not going to propagate very well outside of homes. 2.4 goes pretty far outside of homes a lot of times. 5 gigahertz goes less outside of the walls. It does reach out somewhat. And then 6 gigahertz even less. So it should be that if you've got these devices at a lower power indoors, that it's not going to be interfering with incumbents that are in the area. So you can see here, this is from the report and order, you can see the different antennas classes, the standard power and the low power, and you can see the power levels that they're allowed. So in the standard power, you can see that that's the 850 megahertz of operating bands that they're allowed to operate in. And then you've got the low power that can use the entire 1,200 megahertz. So you've got that contiguous spectrum that they can use throughout that whole area, which is very nice. And one last thing is the FCC has proposed a further notice of approved rulemaking, which would be, this is actually part of the report and order, so it's a kind of a second half of it. And they said, okay, now that we've made these decisions, and this is the way we're moving forward with the 6 gigahertz band, we wanted to ask for comment on a few other things. And they're asking about very low power for outdoor use. This would be even lower, and indoor use. This would be even lower than the power requirements for the low power antennas inside. And this would be for use, let's say, outdoors with no AFC required. So you could have this antenna outdoor, this particular access point, very, very low power outdoors. It would allow for very high speeds, but very short range. So an example might be, for example, if you had your phone out there and you wanted to set up a personal hotspot with your phone, kind of tether from that, would allow for that, and other kinds of interesting, maybe applications that people haven't even thought about yet with this very fast, very low latency, but low power kinds of devices. And they're also looking at increasing the power spectral density for indoor use. So currently it's at that 5 dBm per megahertz, and they're wanting to get comments on raising that to 8 dBm per megahertz. And that's just to provide us with a little bit more power in the home. We'll have to see what comments there are. There's probably going to be people on both sides, some that are going to want that to go through, and others that are going to say, no, that might increase the potential for interference. Generally, what you have is your device makers and your service providers are wanting, they're going to want more power in the home or in the business to be able to do more things. And you've got the incumbents that are going to be arguing that, no, this might cause interference. So we'll have to see which way that goes. So this is very exciting. Should be out. Again, Wi-Fi 6 is out now. So there are people that, there's equipment out there, people using it, I believe, already. There's equipment out there that's using Wi-Fi 6, but just didn't have the 6 gigahertz capability, or maybe they built it in and it's not turned on. But they will be able to get that certified and then be able to have a little certification that they are Wi-Fi 6E certified. And this equipment should be coming out probably before the end of the year. So you'll start to see some of this 6 gigahertz Wi-Fi stuff coming out before the end of the year. That'll be great. What kind of benefits do we have? So if you're talking about, the way you're talking about this very wide bands and high bandwidth, and really the key factor also is this pristine spectrum that nobody is using, because as you know right now, probably if you're ever having Wi-Fi congestion, it's because you've got so many devices on the same channels in your home, plus you might have neighbors that are using the same channels on the 2.4 and the 5 gigahertz. At one point, 2.4 got really congested, and then 5 gigahertz came out, and it was new and it was a lot less congested, but now there's a lot of devices on 5 gigahertz. So this is brand new, 1200 megahertz. You can have all these separate channels where there's no overlap. Again, 120, was it 320, 160, excuse me, 160 megahertz wide channels, and maybe a 320 at some point. But at 160, I think, what was it, 7 channels that you can have that don't overlap, or you can have 14 that don't overlap at 80 megahertz. So that's really kind of a big deal. And you look at MDU in office environments. So you've got an apartment complex, and you've got everybody, let's say, in the complex has broadband, and they're all using Wi-Fi, and you've got these Wi-Fi signals leaking between walls of different apartments, and you've got all this contention, and it just makes for slow internet service. Most of the time when you have slow internet service, it's not your broadband operator, it's your Wi-Fi in the home. So unfortunately, that's the problem that we have today, but this will be resolving that. It's going to be great for cellular network offloading. So most of the internet traffic these days is going over Wi-Fi, and it's going to be even more so the case now. So a lot of times when somebody's on their cellular network, they go somewhere and they are suddenly on Wi-Fi. When you're in your home, a lot of times you're on your Wi-Fi network. You're not going over your cellular network. If you're around a hotspot somewhere, you might be on your Wi-Fi network. So this is going to help with cellular networks on offloading a lot of that data. And then also, Wi-Fi backbone in the home is another opportunity, because right now what most ISPs do, if a cable company or let's say a fiber provider, they'll have their cable modem or their ONT somewhere in the home, maybe on a wall or on a desk near a wall. And then a lot of times they won't have an integrated router. Maybe they'll have their CPE, and they'll have a separate router connected with a piece of Ethernet cable. And the problem with that is, again, a lot of times it's kind of on the perimeter of the home where the wire comes in. But in this case, they could have the wire come into the CPE, and the CPE could have a 6 gigahertz radio that communicates with a router somewhere centrally located in the home. So you can maybe get better internet service throughout the home by having that router be centrally located. This will also complement, if you think about 5G and 10G. So 5G is the 5th generation of cellular service. 10G is what Cable Labs is calling basically DOCSIS 4.0, which would be really 10 gigabits per second is what the G stands for there. And both of those are very fast, and then DOCSIS 4.0, both 5G is very low latency. DOCSIS 4.0 is going to be low latency with low latency DOCSIS. So you've got this very fast, very low latency connection coming to the home, and then you can have very fast, low latency connection within the home. Because right now, with the regular Wi-Fi we have, it's going to be your standard latency and speeds. So this will be very complementary to 5G and 10G. Wi-Fi 6 and 5G, a lot of people are kind of pitting them against each other, but they're not really. The 5G is really more for mobile cellular kinds of applications, and Wi-Fi is really tends to be fixed area kinds of communications. So they are different, and they complement each other well. You've got some interesting things you can do with wireless gaming controllers as you get these fast speeds and low latency. Maybe you've got just a wireless controller that you use that connects to a gaming system in the cloud. Augmented and virtual reality. So you could think of a situation where instead of watching, pulling up Netflix and watching a movie on a big screen, maybe you're watching it on a virtual reality headset or an augmented reality. You could be doing augmented reality work using some glasses where you can actually see things in addition to what's in front of you. You can see the augmented reality as part of that. So those are all really cool applications that are coming. I see. Hello, Rick Ginger. Happy Tuesday to you, sir. Thanks for watching. Rick was with me last week, so if you get a chance, check our YouTube channel. Rick was talking with me about deploying fiber. He's a cable operator up in Highlands, North Carolina. He was talking about deploying fiber in new service areas. So that was great. I appreciated having Rick on. So I hope this was helpful for you. If it was, please go ahead and subscribe to our channel. Just click the little subscribe button and ring the bell, and then you'll get notified when we are live. Also, if this was helpful, if you liked the video, please give me a thumbs up. If you learned something about Wi-Fi 6. And again, if you want to know more about Wi-Fi 6, down in the comments section there, just click the link, and you will see a link to my previous broadcast where I talk about the Wi-Fi 6 standard in general and how this is really improving Wi-Fi. It's kind of the next phase or next generation of Wi-Fi. And then on top of that, now we're layering this big band of spectrum that we have in the 6 gigahertz range. So thanks for joining me for Tech Tuesday. I will be back next week, Tuesday at 3 o'clock, and I hope to see you then. Bye-bye.